One of the primary limitations on modern space travel is the fuel requirements involved. To launch a rocket a long distance requires a large quantity of fuel. However, such large quantities of fuel weigh down the rockets, in turn increasing the fuel requirements for long voyages. As a consequence, it is practically impossible to produce a rocket that would travel to Mars and back with modern fuels. So I first proposed the idea to connect a 384,400 kilometer gap between the Earth and the Moon using some type of elevator. Yeah, I knew it'd be funny and pretty much impossible, but I still wanted to do it for the laughs. Obviously, the Moon rotates around us at a different rate than our planet spins in its own orbit, so I decided to build a giant gyroscope around the Earth and the Moon, which would hold the long pole that went from the outer ring to deep into the Moon. While I had no idea if we even had enough materials to do it, I still continued thinking about how this whole thing would work. The plan was to have the rocket transported from Earth to the Moon using the elevator. Due to the Moon's lower gravity, it'd take less fuel to launch the rocket from the Moon all the way to Mars. All of this was extremely expensive and costly, and it didn't even really solve the problem of manned exploration on Mars. In order to solve this problem, I figured that it'd be best to find an external source of propulsion that is not on board the spacecraft. A space elevator is a long tower that uses the Earth's natural rotation as a power source for the spacecraft. Like a sling, the tower rotates along the Earth's equator and flings the spacecraft at extremely high velocities, approaching 35 kilometers per second, or 78,000 miles per hour. In comparison, the SpaceX Falcon 9 rocket moves a paltry 41,000 miles per hour, 17 times slower. In order to attain such high velocities, it is necessary for the tower to extend beyond the Earth's geostationary orbit, the orbital distance at which the centrifugal force from the Earth cancels out the Earth's gravitational pull. To meet this requirement, the minimum height of the tower would be over 22,000 miles. The tower shown extends 27,000 miles above Earth's surface, which is over 52,000 times as tall as the Burj Khalifa, which is the world's tallest building. In order to prevent Earth's gravity from pulling the tower down from space, a large counterweight needs to be placed at its end. The centrifugal force on the counterweight overcomes the force of gravity to keep the tower from collapsing. For a tower of this length, a massive sphere of iron weighing over 1 million metric tons will be required to anchor the tower. So this is the editor that I used to put all this stuff together. Over here we have the Earth, and then we have the Moon's orbit, and over here we have Mars. And right here we have two lines. And so in order to launch to Mars, the launch must be timed during Mars' opposition, which is a couple-week gap that comes every 2 years where the Earth and Mars line up in their orbits. So, as you can see, as time goes on, they line up right now, right when Mars gets that 17.5 degree head start of Earth right here, which is that line. And then this line right here is the trajectory of the pod when it is launched, which will take about 55 days. So it goes up until there. This equation shows how we did not use the most direct route in between the Earth and Mars when we shot the space pod. Instead, it approximately aligns with the motion of the Earth in order to utilize the Earth's motion about the Sun as a propulsion source. The tower endures immense stresses as a consequence of the gravitational force of the Earth, as well as the centrifugal force caused by the counterweight at its end. To withstand these forces, the structure will be made out of carbon nanotubes, also known as CNTs. They are the strongest material ever discovered, able to withstand 150 million metric tons per square inch of fiber, and that's 2.5 times the 10th strength of diamond. This is the equation defining the width of the cable. A tower of these dimensions would be capable of launching a spacecraft as far as Venus or Mars. It would be impractical to make an elevator that can reach Jupiter from Earth because the pole would have to be twice that of the one that can reach Mars. One of the primary benefits of the construction of a space elevator would be its ability to provide easy access to Mars. Relative to the Mars rovers, the craft from a space elevator would be moving 6 times faster and along a more efficient trajectory due to the lack of fuel requirements. Because the spacecraft will be moving much more rapidly than other Mars landers have moved, the landing process will have several stages. First, counter rockets will fire in order to drastically slow down the craft. Then the parachutes will be deployed, and then after that we will have balloons to cushion the impact. Once the spacecraft lands on Mars, it will unravel to reveal whatever contents are inside.